So to control the burning of hydrogen and oxygen, we use carbon as a backbone, as a skeleton of biologic molecules. Carbon in biologic systems is the backbone. That's where the word organic comes from. Yeah, at Whole Foods, organic means something, all right? In science, organic means there's carbon in it that behaves in a biologic manner. And so organic carbon is the backbone of biologic molecules, quite simply, so we can burn in a very efficient, stable, and renewable manner. So we can utilize energy in a very stable manner. All right? Wood is a type of hydrocarbon. If you put glucose molecules together in a certain arrangement, you have starch. If you put them together in a different arrangement, it's cellulose. Right? We don't eat wood, fortunately. But if you burn the wood, all that white stuff is phosphate, but the black stuff is carbon. And the oxygen and hydrogen have been burned up. But the oxygen and hydrogen were not in gas form. They were in a molecular form, and you guys know it as glucose. Right? And we call that a carbohydrate. All right? And so if you look at a glucose molecule, you'll see it's this carbon ring with, you'll notice, water molecules on either side of it. And we can combine the hydrogens and the oxygens together to release energy. And water is the byproduct, and carbon dioxide. We make carbon dioxide too. And carbohydrates, the sugars, the starches, cellulose, these are all carbohydrates, and they're created by plants using something called photosynthesis. And I'm pretty sure we started this lecture talking about capturing the energy of the sun. How did those people know that stuff? Okay, hydrogen makes one covalent bond, oxygen makes two covalent bonds. I think I've kind of explained that. Let's talk about carbon. Carbon's a very unique substance. Pure carbon can be a black powder like coal or graphite. We can take pure carbon, make a diamond. In biologic systems, carbon is the backbone of biologic molecules. They won't even draw it. And you'll notice that the carbon makes 4 covalent bonds because carbon has 4 houses of electrons that are single. So it can make 4 covalent bonds. The interesting thing about carbon is once those 4 covalent bonds are made, carbon doesn't have one side that's more negative and one side that's more positive. That's why hydrocarbons repel water, because those 4 covalent bonds don't leave an extra set of electrons somewhere. Right? So carbon makes 4 covalent bonds. Like the hydrogen gas methane, here's methane. Notice the carbon is making 4 covalent bonds. Each of those lines are little covalent bonds. Notice each hydrogen is making 1 covalent bond, just like a little building set. Right? So there's my methane gas, my methane molecule. Here's the gas carbon dioxide. Notice the carbon is making 4 covalent bonds. Notice each oxygen is making 2 covalent bonds. CO2, carbon di-2 oxide. So there's my carbon dioxide molecule. That's where all this word comes from. They throw these words around like you guys know everything about this. You look at a pharmacology book, they'll draw the chemical structure, and they won't even put carbon in it because it's the backbone of the biologic molecules. They won't even draw it. They assume that you know that it's there. So we know the rules. 4 covalent bonds for carbon. Anything missing must have a hydrogen because it makes 1 covalent bond. I don't expect you to know this, but look, this is how they'll draw something called furan. I don't need you to know that. But if they drew a furan ring, they draw it just like this. And you're like, well, what is that? Okay, well, that's the oxygen. All right. And each of those lines is a covalent bond being made by the thing that's either drawn or the carbon that they won't even include. Now, each carbon needs to make 4 covalent bonds. Notice the oxygen's bonded with 2 carbons, but the carbons are only making 2 covalent bonds. They need to make 4. So that means that's where the hydrogens are. So this is what it'd look like if they sit around and spend a lot of time with PowerPoint. Right? If they don't, they draw it like this. Okay? So this is that, Okay? So that's what I want you to see when you look at this. They don't even draw the carbons. Each of these is a covalent bond being made by a carbon that's not even drawn. Okay? I don't make this stuff up. This isn't my fault. We've got to talk about oils, lipids, fats, waxes, hydrocarbons. They are hydro, water, phobic, not liking. Phobia is being afraid of something. And so we call oils, lipids, fats hydrophobic because they're repelled by water and they're afraid of water. Right? Same word, lipophilic, fat-loving. Hydrophobic is the same thing as lipophilic. Fat-loving is the same thing as hydrophobic. So be careful with the words. Hydrocarbons are carbons with hydrogens. Carbohydrates are sugars and starches. Okay? Hydrocarbon, hydrogens on the carbons. Carbo, what is hydration? Water, right? So when you look at a glucose and you see the carbon ring, you'll notice that on one side of the carbon is a hydrogen and on the other side of the carbon is a hydroxide. And that's where carbohydrate comes from. Well, they talk about saturated fats on TV like everybody is some kind of chemist. So when something is saturated, it just means the carbon chain is completely full of hydrocarbons. That means there's no double bonds in the carbon chain. So when something's saturated, when a hydrocarbon is saturated, like a fat, it's easier to stack them together very nicely like corrugated roofing and stack them neatly right against the walls of your arteries. It's more complicated than that, but it's a great story. All right. Unsaturated fats mean there's double bonds in the carbons, meaning they twist and turn, their chains twist and turn, meaning they can't be stacked together real well against your arteries. Right? So that's what that saturated and unsaturated thing means. All right, we're talking about hydrocarbons. There's methane, ethane, propane. Propane, the same propane that you can't buy 2 days before a hurricane. All right? Because of people like me. All right, there's propane. Octane, same octane that gets you the numbers on the gas pump, right? All that stuff burns. All right, so hydrocarbon chains are not polar. That means they repel water, they repel ions and other substances. So molecules that are not charged or polar are considered lipophilic. They like fatty, oily, waxy, greasy molecules. I think we all know this, and I've already talked about it. And they talk about this stuff in the chemistry books, like you know everything about this. Let's talk about aromatic rings. We're going to talk a lot about aromatic rings. In aromatic rings, the carbons will shift their double bonds from carbon to carbon. So notice they didn't even draw the carbons on this aromatic ring. And we notice that each carbon is making 3 covalent bonds and it's shifting. So there must be hydrogens around the outside. So there's the carbons and there's the hydrogens. Right? These are very stiff structures. They're used throughout biologic systems. All right? The aromatic rings will be drawn like this. I want you to recognize them when you see them. Okay? They don't draw them like this. They draw them like this. Aromatic rings are everywhere. Like tyrosine, an amino acid, we're going to make epinephrine, norepinephrine, and dopamine out of tyrosine. Right? It's an amino acid, so it's going to look like this, and this is the aromatic ring. There's the amino group, there's the acid group, there's the aromatic ring.